Shanghai Astronomical Observatory, and today I'm going to talk to you about some study we have been working for some time, and it's mostly still ongoing work. And this is to look at the low surface brightness galaxies and AGNs. And so the definition of the low surface brightness galaxy is quite arbitrary. It probably originated from the old Freeman law, where which states that there are limited number of galaxies with very low surface brightness. Even though this statement is proved to be not correct, but people are interested in looking at the surface brightness galaxies that are 1 magnitude fainter than where used to be the peak here, to see whether they are intrinsically a different class of galaxies, or are they mainly just a tail of a normal galaxy. So that's exactly what we are trying to also look into here. So originally we only wanted to study just a few low surface brightness galaxies to look very carefully of their two-dimensional properties, and then quickly we found that nowadays there's not a quite consistent and a big sample of catalog that we can actually choose from and compare of. And because from the SDSS galaxies, and people have studied trying to build a catalog of low surface brightness galaxies, the way they do back then, they don't have the detailed bulge disk decomposition method, so they just, the way they did it is just to assume that the galaxy is a pure exponential disk and get rid of, just ignore the galaxies that might have big bulges, and then use the total magnitude to estimate the extrapolated central surface brightness. And we realized that this could be a problem for a lot of galaxies that have bulges in there. So having seen that there are now available catalogs that have done this bulge disk decomposition, and so we decided to look into the possibility to select low surface brightness galaxies of a large sample using these online bulge disk decomposition catalogs from the SLO. And we know that when you do these things to a large samples, you could have problems. So to be sure, we selected about 100 galaxies randomly from this big Sloan catalog, and did a Gauss decomposition analysis carefully to get their bulge and disk properties, and trying to compare these online catalogs. And this random selected 100 galaxies. They are mostly having lower redshift and lower stellar mass, but their specific star formation rate seems to be consistent with the big SDSS catalog. So after we did this, we compared with what we with this online catalog, and the general conclusion is that it looks like the bulge disk decomposition in deriving the bulge properties are quite problematic as shown in the upper panel. But for the disk properties, it seems that they are okay. Roughly, they are consistent with what we did with extended Gauss analysis. So since the selection of the low surface brightness galaxies are mainly on their disk properties, because this central surface brightness is mainly the central surface brightness of the disks. So we decide that since the disk properties are okay, it seems that we are okay to use this bulge disk decomposition to select our low surface brightness galaxies. And of course, we also need to be careful, because some galaxies you probably don't need this two-component phase bulge versus disk. Some galaxies are purely like just pure disk galaxies. So fortunately, in this catalog, CMARS catalog, there is a parameter called PPS, which is that when they are small, less than a certain number, basically that means that this fit does require the two-component fit. And in that case, we use the two-component model and derive their disk properties. And if this parameter is, this is larger, larger than this particular criteria, we use a one-component model. And since we're interested in disk, we ask the surface index of less than 1.5. So this is a comparison of these two-component fits of CMARS catalog versus a Galaxy central surface brightness comparison, and you can see how different they can be if you just adopt the Galaxy selection criteria to select low surface brightness galaxies. So this is just to show a few stamped images of the high surface brightness and low surface brightness galaxies that we found in this sample. And so when we plot their mass distributions of these low surface brightness galaxies and the high surface brightness galaxies, we found that for the low surface brightness galaxies, you clearly see this bimodal distribution in their mass. And we were careful, we are trying to confirm, double check whether this bimodal distribution is actually a natural one, or it's just due to our selection effect. We are still checking it, but it looks like our selection of this p-cut here, this PPS parameter, seems to be not affecting this distribution to have a bimodal distribution. We changed that criteria for some other values, and this stays. And this is their mass star formation rate distribution. And it looks like the low surface brightness galaxies, the reason they show this bimodal distribution is probably because there's a deficit of galaxies that are in this region. And galaxies are preferentially located in the upper range here and in the lower star-forming region here. So we are still checking whether this is purely a selection effect or something in real. But among these red low surface brightness galaxies, people have before studied a particular type of low surface brightness galaxy, which is called the giant low surface brightness galaxies, and seems to be quite unique and interesting. And the definition of this giant low surface brightness galaxy is that asking the surface brightness versus the radius, sort of the scale length plot, satisfy a certain value, which means that for this kind of galaxies, their disks have to be low surface brightness in the center, and also the scale lengths have to be large. So these are like galaxies with very large extended disks and also low surface brightness galaxies. And it looks like only a few of them, of these so-called giant low surface brightness galaxies, have been studied extensively, and it seems that they are dark matter dominated, have very massive H1 disks, but their gas surface density in this disk is lower than this critical density required to form stars, so their specific star formation rate is very low. And the DP images also show that they show this extended faint disk. One of our collaborators have done a study on a very small sample of this giant low surface brightness galaxies. These are a sample that with a giant low surface brightness galaxy but have an obvious AGN in the center, which shows this broad H alpha and H beta emission lines. And they used the emission line width to estimate the black hole mass. And it looks like that when you plot the M sigma relationship, it seems that they are significantly off to the M sigma relationship, the standard M sigma relationship. But so what we are doing is on this sample, and the fact that they are having this AGN activity in the center, which basically shows that the bulges in this giant low surface brightness galaxies are kind of matured one. And what we are trying to do for this sample is to do a bulge and disk decomposition on these galaxies. and to study the bulge properties and the disk properties separately. And as a result, we found this. So the red points are the properties are the bulges of these giant low surface brightness galaxies, and compared to the local early type galaxies, it looks like they are preferentially more compact. And when we plot them into the size mass diagrams, it also looks so. And so these the lines are taken from the Van der Waal et al. At 2014, which actually tells you where the early type and late type galaxies are located at different redshifts. And it seems that the bulges of these giant low surface brightness galaxies that we are studying seems to be quite compact compared to the local early type galaxies, and are more similar to the higher redshift early type galaxies. So yeah. So these are things that we are still checking to confirm whether this result is robust. And in the meantime, we are also interested in looking at the environments of these low surface brightness galaxies. And a couple of years ago, in our group, we have a postdoc who nicely developed this void catalog from the SDSS. And this is based on the SDSS data release 7, and use the void algorithm to find the void structures and the wall structures. And at the end, in a volume limited sample, they find about 1,000 voids. And in these voids, there are almost 80,000 void galaxies. And one of the main conclusions is that the void seems to fill up about 63% of the volume. So now we are having this low surface brightness galaxy sample. We begin to correlate it with the void catalog. And before we do that, we also separate the low surface brightness galaxies into a red low surface brightness and the blue low surface brightness galaxies, very roughly using a dashed line here in the center, and see how they are different. And what we found is that so this is a plot of the fraction of the low surface brightness galaxies, which is a number of low surface brightness galaxies we selected as a blue low surface brightness galaxy and a red low surface brightness galaxy divided by the whole galaxy in each of these beams here. And this beams means that the distance to the center of the void. So you will see that for the void galaxies, which are shown here in the solid curve, the distance to the center of the void is low, but they are over 2. So I want to explain this because many of these voids are not exactly spheres, so they could be multiple spheres adding together. So you would find, but here in the R void, the radius of void, we use the sphere. So you could see cases where the distance to the center of the void are larger than the radius of voids. So that's okay. So you will see that these curves of the inner voids are more or less to the left, and the inner walls are more or less to the right. But in general, it looks like there's a slightly higher fraction of blue low surface brightness galaxies in the voids, and there is a significant higher fraction of the red low surface brightness galaxies in the wall region. But the general trend, the trend of the fraction seems to be similar as a function of the distance to the void regions, void centers. Okay, I'm actually done. These are the more or less what we are doing right now, and this is a summary. So we use the catalog that have decomposed the bulge and disk properties to select a sample of this low surface brightness galaxies, and it seems that for a sample of the giant low surface brightness galaxies, the bulges are compact compared to the local early type galaxies. And compared to the environments of this sample, it looks like the blue low surface brightness galaxy fraction in voids is higher, and while it's contrary for the red low surface brightness galaxies.
Thank you.
I missed how it is that in the giant low surface brightness galaxies at a given mass, they have small radii. They are compact, and yet they're low surface brightness. How do we do that?
Oh, so it's compact in the bulges.
The bulges.
Yeah. So I only so if you just compare the bulges, so we have a very bright and compact bulge, but extended disk. Oh, okay. So yeah. Sorry, we didn't plot the error bars. The fraction comes more or less you can see it from here. This is a total. This is a red low surface brightness galaxy. This is a fraction of the blue low surface brightness galaxies, and the number in the overall catalog of galaxies are listed here. So we didn't plot it in the error bar. Yeah, here we didn't show it here. So this is the conclusion is that it's not that significant. It's not, but here it's significant. So this is obviously off the arrow, but here it's not that significant. Just a slight trend here. We haven't checked that. We'll probably check. There's a lot of things to do with this catalog, so we're doing this. Yeah.